Hello, this video is on orders, sizes of finite matrix groups. The order is the first invariant of a finite group, and here we will examine finite groups of matrices. And to have a matrix group finite, it helps to assume that the number of coefficients of scalars is finite. So our field is going to be finite. Let's take a prime and look at the numbers mod p. And that will be the field of p elements. So that will be denoted by f sub p, but that will be integers modulo p under addition and multiplication. And sort of all the linear algebra will involve finite number of things. If we're dealing with if we're doing linear algebra over this field. So, for example, the number of vectors in the coordinate and dimensional vector space over this field will be just this power of p. And that is a consequence, an immediate one, of the multiplication principle, because these vectors, by the very definition, they are elements of the Cartesian power. They are elements of the Cartesian power of n copies of our field. And then the multiplication principle says that the number of elements in here is the same as a product of the number of elements in each of the coordinates, and we have n such coordinates, and hence the answer. But we are interested in computing the order of the general linear group with coefficients in this finite field. And the more compact notation for this is GLN of P. So that is just the replacement for this prime field of characteristic P, so the field of P elements. And that's what we will be counting. We will be counting invertible matrices of size n with coefficients being elements of this field. So let's imagine such a matrix. And then what is it for this matrix to be invertible? One way of rephrasing invertibility is saying that all columns of this matrix will be linearly independent. And how many ways we can choose the first column? And for the whole collection to be linearly independent. Well, the only restriction for the first column will be that it is non-zero. And the total number of columns, so the total pool for columns is this column space. And then we just forbid 0 as a first column. So the number of such choices for the first column of an invertible matrix will be total number of vectors, but without 1, but not 0. Okay, that's how many ways we can choose the first column. What about the second after we have the first chosen? The second column should be not proportional to the first, otherwise they will be linearly dependent from the start and we will fail with invertibility. And if it is not proportional, then there will still be a chance for that whole collection of columns to be linearly independent. How many vectors are non-proportional to a given one, a non-zero one? It's easier to see how many vectors are proportional to the given one, and there will be as many as proportionality coefficients. or another way, proportional to the first vector, they will form a one-dimensional subspace generated by this vector. And so the number of, or the pool of possible second columns will be all columns, but not those which are proportional to the first chosen. So we will be taking out a one-dimensional subspace from our n-dimensional coordinate space. And to count these possibilities, we just have all vectors, but those which are proportional to the first chosen column. And you could see where it is going. So if we now look at the third, for that to be linearly independent with the first two chosen, it should not be a linear combination of the first two chosen. So we have to take out all linear combination of a pair of non-zero vectors, linearly independent vectors, and these two linearly independent vectors will generate a plane, a two-dimensional subspace, and counting elements in this complement of the plane will have p to the n minus p squared. And that will continue till the very last vector, and the very last vector will be linearly independent with all previously chosen, so that number of linear combinations of the previously chosen will be this power. And in the compact form, the order of the general linear group is the product of these differences, p to the n minus p to some power I, and I starts with 0 and ends with n minus 1. So that is the compact answer for the order of the general linear group. Let's now compute the order of its normal subgroup, the special linear group. And the definition of this special linear group is that it is the kernel of the determinant homomorphism from the general linear group to the invertible scalars. And we also know that the image of the determinant, the image of this homomorphism, is the whole multiplicative group of scalars. And of course we know how many such invertible scalars we have. In a field we have everything but 0. So that will be the order of this multiplicative group of the field. And then by Lagrange's theorem, the order of the kernel times the image is the order of the whole group. If we have the subjective homomorphism, well, yeah, we have its image. So yeah, the product of the kernel, the order of the kernel times the order of the image is the whole group, and hence we have the answer for the kernel order. It is the order of the whole group divided by the order of the image. And so that is a quick consequence of this previous formula for the order of the special linear group. We also can compute orders of quotients by centers. They're called projective linear groups, projective general linear group with any coefficients is the quotient of the general linear group by its normal subgroup, which is a center. And we know what is the center. The center is just the subgroup of scalar matrices. So we're quotienting by scalar matrices. And in our finite case, if we want to compute the order, it is again the Lagrange's formula, which will give us the answer, the order of the projective. So it is projective general linear group. And the order in this case of coefficients of size p will be given by the same formula, by the same ratio. It's the order of the general linear group divided by the number of non-zero scalars. And the final computation is for the projective special linear group. It is, as the projective general linear group, the quotient of the special linear group by its center. And the center will be the subgroup of the special linear group consisting of scalar matrices. And the condition now is that these scalars have to be roots of degree n of 1. So the order of the projective special linear group is, again, the quotient of this answer by the order of this group. So let's see what is the order of this group. The count of scalar matrices with determinant 1 is the same as the count of scalars which are roots of degree n. We know that the multiplicative group is for the p minus 1, of course, but it is also cyclic. And this is a subgroup of this cyclic group. And the order of the cyclic group is p minus 1, and we're looking at the subgroup of solutions of this equation in a cyclic group. It has to be cyclic, and the order will be just the least common multiple of p minus 1 and n. Sorry, not least common multiple, what did I say? It's the greatest common divisor, rather, of n and p minus 1. And that's what we have to put here in the answer for the order of the projective special linear group. It will be this greatest common divisor of p of n and p minus 1. That is it for the computation here. See you later.